Hello friends, I welcome you in lecture number 37 on hypothesis testing. In lecture number 1 to 36, we have discussed different types of hypothesis test, and now from this lecture onwards we are going to discuss miscellaneous problems based on lecture number 1 to 36. In lecture number 1 to 36, we have discussed several hypothesis tests and we have discussed the examples related to that particular hypothesis test. But in examination, you will not be given that which test you should apply. So you have to decide that which test is applicable. So from this lecture onwards, we are going to discuss this type of problems in which we will decide that which test is applicable and then we will solve the problem. Here I have taken this question which was asked in GTU Summer 2022 exam. Now before solving this question, the assumption is that you must have understood lecture number 1 to 36. You must have understood a different hypothesis test, that is hypothesis test for population mean, hypothesis test for population variance, hypothesis test for population proportion, and hypothesis test for difference of two means, difference ratio of variances, difference of proportions. Similarly, you might be familiar with large sample hypothesis test and small sample hypothesis test. So you must be familiar with all those terminologies which we have discussed in lecture number 1 to 36, and then only you can decide that which test is applicable for a given problem. But what we can briefly understand is that if we are given average problem related to averages, then we will consider the large sample hypothesis test for population mean. If we are interested in the variability, then we will consider the test for population variance, which uses chi-square distribution. Similarly, if our sample is in terms of proportion, that is something out of something, then we will use large sample test for population proportion. And to apply all these tests, we have discussed several conditions, and you should check whether those conditions are satisfied to apply particular test. In short, you must be familiar with all the hypothesis tests and the assumptions which we make for those hypothesis tests to apply for a particular problem. So with that assumption here that you are familiar with lecture number 1 to 36, I am going to discuss this question. A coin was tossed 960 times and returned heads 183 times. That means they are tossing a coin 960 times, and they find that out of those 960 tosses, 183 times head appears. Test the hypothesis that the coin is unbiased and use 5% level of significance. So here the test is not specified. You have to decide that which hypothesis test you have to apply. So that you can decide from the given information. Here what is the given information? That they are considering 960 tosses of a coin, and out of 960 tosses, 183 are heads. Out of 960 throws, they find head on 183 tosses or throws. So can we conclude from this information that the coin is unbiased? Now here we can see we are given that there are 183 heads out of 960 tosses. So you can have the idea that you are given something like proportion. You are given the proportion of number of heads from given number of tosses, and using this data you have to test the hypothesis that the coin is unbiased. Now when we can say that coin is unbiased or fair? So we know that the coin is unbiased if there are equal number of heads and equal number of tosses on all possible throws. There must be equal number of heads and equal number of tails. Number of heads and number of tails must be equal on each possible toss for the coin to be unbiased. And they are considering the sample of 960 tosses, and out of these 960 tosses they find that the number of heads are 183. So here this is the problem of proportion. We are interested in the proportion of heads in the tossing of a coin. Now if we want to check whether coin is unbiased, then for every toss we must have equal number of heads and tails, or the number of tosses, whatever the number of tosses are there, we must have equal number of heads and tails for the coin to be unbiased. So for that they are considering a sample of 960 tosses, and they find that there are 183 heads. So can we conclude from this sample data that the coin is unbiased at 5% level of significance? That we have to decide. So first thing is, if the coin is unbiased, then there are 50% chances for head as well as tail. So we can say that population proportion must be equal to 50% or 0.50. If coin is unbiased, then we can say that the proportion of number of heads or number of tails must be equal to 0.50. So we will consider null hypothesis as that the coin is unbiased, which is equivalent to the fact that population proportion is 0.50. And negative statement of this is coin is not unbiased. So coin is not unbiased if population proportion is different from 0.50, and level of significance is given as 0.05, that is 5%. And what is the data from this sample? They are tossing a coin how many times? 960 times. And if we consider capital X equal to the number of heads in this sample, or number of heads in 960 tosses, then it is given that capital X is 183. So there are 183 heads in 960 tosses. So this will give us the sample proportion. Sample proportion is given by capital X divided by n. So we have 183 divided by 960, and if I use my calculator up to 4 decimal places, I obtain sample proportion equal to 0.1906. Now to apply large sample test for population proportion, if you recall, we have to check two conditions, n times p and n times 1 minus p must be greater than 5. Here n means sample size is 960, small p means population proportion, which we have assumed as 0.50. So if I find out this product, then I obtain 480, which is obviously greater than 5. And 960 times 1 minus 0.50, 1 minus 0.50 is 0.50. therefore this is also 480. Therefore n times p and n times 1 minus p both are greater than 5. Therefore we can apply Z test for population proportion. We are using Z test for population proportion. If you are not familiar with this hypothesis test, you can watch my lecture on large sample hypothesis test for population proportion. Now what is that formula for test statistic? If we apply this Z test for population proportion, then you can recall the formula for test statistic is sample proportion, that is p hat minus population proportion divided by square root of p times 1 minus p divided by n. Now we are having all these values. Sample proportion we have obtained is 0.1906, population proportion is 0.50. We assume that null hypothesis is true and we are testing that null hypothesis. This is 0.1906 minus 0.5 divided by square root of p, that is 0.5, 1 minus p, that is 1 minus 0.5 is also 0.5, divided by n, which is 960, and using scientific calculator I find that value of test statistic is minus 19.1728. This is my calculated value of test statistic for population proportion. Now next step is to decide the critical values, and here we know that if these two conditions are satisfied, then this random variable capital Z is a standard normal random variable. Therefore the graph of this is a bell shape curve. So let me roughly sketch here graph of standard normal curve, density curve. It is a symmetric curve, bell shape symmetric curve, and our alternative hypothesis is that population proportion is different from 0.50. Therefore we have two-tailed test. Here at the middle we have 0 and level of significance is given as 0.05, and because alternative hypothesis is that p is different from 0.50, that means we have two-tailed test. Therefore we have to divide this level of significance into two equal parts. 0.05 divided by 2, that is 0.025. So I will consider area of 0.025 in left as well as right tail. Therefore these 2 points are z suffix 0.025, this is z suffix 0.025 with negative sign, and these two shaded regions are critical regions or rejection regions, and area in both the tails is 0.025, and we have to determine these critical points or critical values. Now what is meaning of this z suffix 0.025? That means probability that if value of capital Z is greater than this value, which we have to decide, z suffix 0.025 is 0.025. Area to the right side of this point is 0.025, that we can write in terms of probability as probability that capital Z takes the value greater than this point is 0.025. Now what about this probability? Probability that Z is smaller than z suffix 0.025. This is nothing but 1 minus probability of its complementary event, which is z is bigger than z 0.025, and therefore probability that capital Z is less than Z 0.025 is equal to 1 minus this probability, which is 0.025, and therefore we have 0.975. So we are interested in that value of Z for which this probability is 0.975, or area to the left of this point is 0.975. So to find out this critical value, I have to look in the cumulative standard normal table and I have to search for 0.975. So let's use that cumulative standard normal table. Here we have cumulative standard normal table. You can see this point is Z, and this area is probability that capital Z is smaller than this Z, and we have to search for this point Z 0.025 such that area is 0.975. So in this table we are given the areas which are left to the critical point Z. So in this table I have to search for 0.975 and I have to decide the value of small z which corresponds to this area 0.975. So among all these areas I should search for 0.975. So I will search for 0.975. Here this is 0.96 and I am interested in 0.975. Here I have 0.9732 and this is the value 0.9750, and I have to decide the corresponding value of z. So I will consider this row. Here I have 1.9 and I have to go in this column. Here I have 0.06. So my z value is addition of this value 1.9 and 0.06. That means z equal to 1.96. If we consider probability that z is less than 1.96, then we obtain 0.975. So this is our critical value 1.96. So here I can say that z 0.025 is nothing but 1.96. So here I write that therefore z 0.025 is equal to 1.96 using normal probability table. Sometimes table values are given in the question. If they are given in the question, you can use them. So here I have this point z suffix 0.025 is 1.96, and due to symmetry this is minus 1.96. So if our calculated value is greater than this point or smaller than this point, then we are in rejection region and we will reject the null hypothesis. And if calculated value of test statistic is in between these 2 points, then we are in non-rejection region. So let's compare calculated value of test statistic with critical values. If we round off up to 2 decimal places, we have minus 19.17, and what is the location of this point? Minus 19.17. So it is obviously to the left of this point. Here we have minus 1.96. So suppose somewhere here we have minus 19.17. So calculated value of test statistic is less than this minus 1.96. That is, we are in rejection region and therefore we reject the null hypothesis. So now we can write that here calculated value of test statistic is minus 19.17 is less than minus z suffix 0.025, which is minus 1.96. Therefore we reject the null hypothesis. And what is the Null hypothesis. Null hypothesis is that population proportion is 0.50 or coin is unbiased. So we cannot say that coin is unbiased. Therefore, we reject the null hypothesis. Therefore, the sample data does not suggest that the coin is unbiased. We cannot say that the coin is unbiased because we should reject the null hypothesis because calculated value of test statistic is smaller than this. So this is very nice question. All you have to remember is that whenever you have something out of something given, here it is given that we are tossing a coin 960 times and we obtain 183 heads. So 183 heads out of 960 tosses. So whenever you have this type of problem in which you have something out of something, then it might be related to the population proportion. So you have to decide sample proportion using the formula p hat equal to capital X by n, and then if this condition is satisfied, you can apply Z test for population proportion. You should remember this formula for test of population proportion, and then you compare your calculated value with critical value and take the decision. Here our decision is that the sample data does not provide enough evidence to suggest that the coin is unbiased because we reject the null hypothesis. So this is all about this session. I hope you like it. Thanks for watching.